Hey everybody, Professor James Ormord here today to talk about the chromatography experiment. This is the last technique lab that we have for the entire sequence of organic chemistry. So now that we have this lab out of the way, we'll finally be able to start doing some actual organic chemistry. This is yet another separations technique. Most commonly, though, this is used for analytical purposes. It can be used qualitatively, but it's most often used quantitatively. But either way, it's used typically for gathering information, separation of the mixtures. So go ahead and take a look at the different types of chromatography we have here. Before I get started, I do want to mention that chromatography, the word itself, literally means color writing. And people found out a very long time ago that we can use liquids to separate out different colored pigments in plant material. And I do want to mention here, there's a fun at-home experiment you could do with your kids if you have them at home. What you can do is take some plant material. Spinach is really good for this. Spinach has a lot of different pigments in it. Grind it up in some rubbing alcohol and dip a piece of white construction paper in it and then let it hang up. And then the different pigments will climb up the paper and you can see separations. There's other ways to set it up with like a toothpick, but I'll let you guys discover that via your Google searches on how to do that at a demo at home. But let's go ahead and take a look here at the lab manual I have here. Take a look at the different types of chromatography. Chromatography itself is pretty ubiquitous across the science disciplines. It's very commonly used. So here we see that we have gas chromatography, which we're using today. You're seeing there that we have a mobile phase and stationary phase. That is a common thing that we see in all chromatography techniques, no matter what exactly you're doing. You always have these two things. So essentially what it is a mobile phase is something that's pushing stuff through your system. And a stationary phase is something that your analytes, your compounds of interest, can kind of adhere to. It works out that because compounds have different physical and chemical properties, they may interact with the stationary phase at different rates. So this is what I'm trying to show here with this bee and hornets analogy. So you can imagine here we have the analogy of we have a group of bees and hornets flying together as a swarm over a bed of flowers. And you could think of their flight path being your mobile phase, and then the stationary phase can be the bed of flowers. And so it turns out that bees have a tendency to interact with the flowers more than hornets do. So as we're seeing here, over time, they start as a swarm, and then as they pass across that same stationary phase, over time we'll get a net separation. That's effectively what we're doing here today in today's lab. We're going to be doing about two techniques, gas chromatography and thin layer chromatography, and they're both commonly referred to by their acronyms GC and TLC respectively. So looking at the table here again. So here we see gas chromatography. The mobile phase is the inert gas. Inert gases such as helium, argon, nitrogen, air is often used sometimes. Something that's not going to interact with analytes. And then we have a solid phase. That is our column. It's going to be a column inside of an oven that we're going to heat it up, but we'll take a look at that when we do the actual experiment. Thin layer chromatography is the one that we're doing today, commonly referred to as GC. Our mobile phase is going to be an organic solvent. You guys will see that in the demo here in a few minutes as well. Our stationary phase is a silica gel plate. I actually have some right here. Essentially, all they are little pieces of plastic. They can also be aluminum with some silica gel. They typically come really long, and we'll cut them down the middle just to make sure they're short enough to fit into the container. I'm going to be careful now not to touch this with my bare hands because you don't want bare hands to touch TLC plates because the oil in your skin will show up on the plate. So please be aware of that. Wear the gloves, and it's not for necessarily safety. It's meant to not mess up your data. Okay, so before we get started on the actual experiment, I did want to show you a little demonstration that give you more of a visual representation of what chromatography is, the separations of colors. So what I'm going to go ahead and do here is I'm going to spot a TLC plate that I'll show you how to use here a little bit later. But I want to just mention here that I have a few things I'm going to try to separate. So I have a couple dry erase markers. So I'm going to use a black and a purple. And then I have this highlighter marker, a regular Sharpie, a wax pencil, and a regular pencil. And I'm going to run them with isopropyl alcohol. So we're going to see if we'll get any separations of pigments here today. Okay, we're about ready to go here. Just to reiterate here, we have all these different writing utensils here, and I spotted our TLC plate with some of each. And I actually lined them up here in the order that they are on the plate. And then for our solvent, we are going to be using isopropyl alcohol. Common name is rubbing alcohol. So all we do is to set it in here and wait. And I will time lapse this part, don't worry. Remember, we want this to be, our dots to be above the solvent level. That. And I will go over this in full detail when we get to the actual experiment part, but this is pretty much what we're doing for the experiment today, except we're going to be doing different compounds here, not markers. Okay, I let this run for over an hour. It took forever, but here is the final result. So that first little spot here that we see all the different colors in there, that was the black Sharpie. I'm trying to see the different pigments inside the Sharpie there. You didn't think that Sharpie had black had all the colors in it, but it does. We're seeing some of the other ones didn't really move all that much. The highlighter moved a little bit. But we're noticing there that the wax pencil and the regular pencil did not move at all. So essentially anything that doesn't move on this plate can be used for your spotting, your line drawing, but remember we're changing the solvent. So if you were to put this plate in the same solvent we're using in today's experiment, other ones might move, this one might move differently. It's all depending on the solvent that you're using. I want to go ahead and start off by talking about the gas chromatography instrument. This is, like I said, a GC or a chromatography technique. We use the inner gas as our mobile phase, and we have a silica gel column as our stationary phase. So in the manual here, I do have a schematic of the instrument. We'll see the actual instrument itself too here in a little bit. Taking a look here, we have a injection port here, your syringe. This is actually on the top of the actual instrument. And then we are going to be pushing it through a rubber septum. And then this is heated enough so that whatever liquid you have in there is instantly volatilized, meaning it goes to the gas phase. And that way the helium gas, can push it through the system. It turns out that how fast they come off is a function of their polarity and their mass. It turns out in today's lab, all of them have a similar polarity. Yeah, they're technically a little bit different, but they're similar. The main deciding factor in today's GC experiment is their mass. So be aware of that when you do the part later in the experiment. You're going to have to figure out which peak is for which one. They're by mass. So this is an example of what GC data looks like. We call it a chromatogram. And here we see these different peaks. So along this x-axis would be retention time. That is how long it took for the compound to come off of the instrument. And if you think about it, the faster it comes off, the less interaction it has with the stationary phase. The longer it takes to come off, the more interaction with the stationary phase it has. If you have a situation where they're all coming out together, there's a couple of factors there that can affect that. One is your carrier gas can be going too fast, and you're not giving the compound enough chance to actually separate. You're just pushing it through too fast. Or they're not different enough, and you don't get good separations based off your medium. Changing your solvent, changing your column can help with things like that. But in today's lab, it's already been done for you. We know which gas works, which settings work to separate the three compounds today. And I just want to mention here the three compounds we're separating are 1 propanol, 1 butanol, and 1 pentanol. They're all alcohols. They're all polar organic compounds. The main difference between them is their mass. So here's our chromatogram again. I will talk about data interpretation on these in a little bit more detail later, but I just want to talk in general for now. So we have retention time along the x-axis, and then whatever response from the instrument on the y-axis. Typically millivolts, things like that. The units on the y on a chromatogram do not matter. And we'll see why in the calculations, why later does not matter. Here also in the chart, I show you some examples of bad data versus good data. So if you're getting good chromatographic separations, typically your peaks will be normal and narrow. Remember, the narrow these are, the better the separations are. And here I'm showing a tailing effect. Basically what that's showing there is the tail dragging. And it means that your compound is hanging up on the column a little bit longer than it should be for good separations. Another common mistake we see on chromatograms is this type of data. This is the case where we're seeing that data overlaps, and there's ways to interpret data if they're overlapping and how we interpret the different areas. It turns out that the area under the curve of each one of these, you remember the integral value if you're taking your calculus courses already, the integration of these peaks here is proportional to the percent composition. So if for example, you had a 1-to-1-to-1 mixture, it should work out where if you added up the areas of all of those, each individual area would have been 33% of the total area of all of them. So what you're going to have to do today is we're going to be calculating percent composition by two different methods, and we're also going to take a look at a percent error calculation. Make sure that you actually communicate to your individual lab instructor on what exactly they want for calculation for the GC, as all of us are a little bit different on what we ask for. So I'm just going to go over what I would normally ask my students to do, and then you ask your actual instructor if they want exactly what I said in the video here, or if they want something different. Okay, let's go ahead and take a look on how we interpret GC data. Okay, so here I have some pretend data that I just drew by hand just to give you an idea on how we're going to interpret our data. So I recommend that you get a colored pencil or pen and a ruler to do this with. So the first thing I'm going to show you here is the triangulation method to get the areas. So the triangulation method is essentially assuming that each one of the signals is a triangle in shape. This is an approximation because it turns out that real data, unless it's really good separations, don't often look exactly like triangles. Like these are not exactly triangles. I'm going to approximate a triangle. And I'm just going to use a ruler to draw a triangle shape with a flat bottom. You don't want an angled bottom, you want it flat on the bottom for your area calculation. All right, oftentimes in real data, you'll have this peak right here. And if you have a really sharp peak that comes out like almost right at the start of your data, that is oftentimes an error peak. So that's your error peak, and what's causing that is that when you actually plunger the needle in there, you're pushing a really small amount of air into there, and as you'll see today, GCs are very sensitive instruments. It can detect when even air has passed through it. So we essentially ignore that peak. So here we're going to go ahead and call this signal A, signal B, and then remember retention time is along this axis. It's typically shorthanded as TR. It could be in minutes or seconds. Our data today is actually in minutes, I believe. Okay, so for here, I'm going to go ahead and draw in a baseline for all of this and try to get it as flat as I can. Okay, at the bottom of these triangles. I purposely drew them to appear to be telling a little bit. So then what I do is I just try to make the best triangle I can that encompasses the most of this line. I don't want to go from, say, like right here to right here, because if you think about it, you're actually overestimating this extra volume in there. And I like to be on the air of caution and kind of underestimate it here instead. So it looks to me like about that is going to be good. And yeah, this is prone to error. We are doing this by hand. And you don't. And here I'm going to go along this way because just like before, if I bring it from here all the way up, you're not showing under the ruler there, but I'm overestimating the volume again. Sorry, the area under that again. So try to get it the best we can, like that. Roughly, we got a little bit of an underestimation here, but I will then measure this here. That is our base. And then we're going to measure the height. H. Like so. And if you guys remember from your basic geometry classes, the area of a triangle is area is equal to 1/2 base times height. You will then take your values here, as long as the units are the same for all your measurements, so you can be in inches, centimeters, kilometers, whatever, as long as you're the same units, it doesn't matter. Things will cancel out later on. Another way I've heard people doing this is doing base times height at 1/2 is another way to do this. So essentially what they'll do is they'll measure the height at 1/2, or the width, the distance of the base at 1/2 of the height. That's another way to do that. I don't like doing it that way. I think that leads to more error than we're already getting here. You would then do this for each of the triangles. And then after you have the area of each individual triangle, you'll then calculate a total area. So we know that total area is equal to the area of A plus the area of B plus however many signals you have. Our actual data today is going to have 3. So it's going to be plus C as well on your actual data today. To then get the percent of A, of just A, you're going to take the area of A and then divide this by the total area times 100%. So remember, just a moment ago I said the units don't matter on your measurement, and the reason why is because as long as you are consistent, the units here will match, they will cancel, and then your unit left behind will be percent, which is what you want. Okay, there are 2 other ways to measure this. One is you're not going to, unless you have a scale at home, you're not going to be able to do this, but I would have you guys do this in lab, would be to cut out with some scissors the actual triangles and then weigh them on a scale and get their mass and use their mass as if it was an area. I know it sounds silly doing it that way, but that method is actually more accurate than this one, depending on peak shape. So if you have a really thin peak, a really narrow peak, it's really hard to get a good triangulation approximation. Cutting it and weighing it's actually more accurate. Additionally, if your peak is not exactly a triangle shape, the cut and weigh method is more accurate because we're not assuming a triangle shape, we're just cutting out the actual shape that it is. So I would then have you guys calculate a percent difference between those two, but you're not going to have the data for that. What you are going to have the data for, though, is the actual data that spits out from the instrument. So I will give you guys a screen capture of this after the actual data is collected, but I just want to show you what it looks like here. So this is a report from the instrument. Here are the results, or retention times, and then the area counts. These are unitless on here, but we're going to use them as if they're areas here. Okay. So what I would have my students do in this case here, remember ask your instructor to see if they want it this way, is I would have you guys calculate what the percent composition should have been from the actual volumes of the different alcohol that we have in there. I think it's 2 to 2 to 1. You'll see in the actual later part, but you can calculate what it should be, and then you calculate what you got from the data, and then do a percent error calculation, just like you did back in your freshman chemistry course. And hopefully you guys remember how to do percent error calculations. If not, there's Google. And another thing people can do here is they can do a percent error calculation with these numbers and treat these numbers as if they're the true values and get a percent error calculation from these compared to this. That's another way to do it. I would argue that the percentages from these ones are probably better because, as you'll see in the video, the vial that we used was some random vial that was sitting in there, and we have no idea how long it was in there. So we don't know if the actual volumes on there are still accurate or not. So we'll see. Okay, so I think you guys now have enough to interpret the data. And as I mentioned a moment ago, the actual data will be, I'll have a screen capture of it at the end of the video after the actual GC part of the experiment.
Hi, so this is Professor Garner. I'm going to help you guys do some instrumentation using the gas chromatograph. So we have actually two gas chromatographs that are hooked up to the same computer system. One of them is on and hot and ready to roll. So each of these have a detector that will determine the signal when it comes out, but the compounds need to be separated. And the way the compounds are going to be separated is by pushing them through a capillary column that will separate compounds based on their mass and their retention time in this column, and they are pushed through with a ultra pure helium carrier gas. Inside the gas chromatograph, there's a column oven that heats up that column, and then the compounds will take less time to travel through as the temperature increases. At the top of the device, the gas chromatograph, there's the injector port. This injector port is kept hot so that the sample vaporizes as soon as the needle is injected, and so the needle goes in through a very narrow opening through a what do you call it?
Septum.
Septum, thank you. And the rubber septum keeps a seal so that the carrier gas doesn't leak out. You have to push the plunger all the way down or the needle down inside, and then this little raised piece here is the trigger that tells the instrument to start the run. So you're going to see when I inject on the actual live instrument that I'm going to put the syringe needle all the way down until this toggles down, and then I'm going to tap the top of the syringe to inject the sample. So these machines are so sensitive, we actually have to use a very small syringe that it could deliver up to 10 microliters, but we only need to inject about 0.1 to 0.2 microliters because too much will saturate the detector. And so what we have to do every time we use a syringe is we have to make sure that it's clean from any prior sample. And so I've got some methylene chloride here, and I'm just running it up and down to rinse out the syringe. Once I've done that, I'm going to get some sample. So I've got a mixture of propanol, butanol, and pentanol. And when you load your sample, you actually have to run the plunger up and down several times to get the air out of the syringe. It may take a longer time for some, depending upon the viscosity of the sample. So I'm actually running this up and down, and I'm looking along the side to see if there's any air coming in. You can actually see when I pull back the syringe, if I pull it back too fast, that there's air right below the syringe or the plunger tip. And so now if I keep doing that long enough, then I don't get any air in the syringe. So I want to pull in extra, and then what I want to do is I want to bring it down to the level that I want, which I'm going to go to like the first division mark on this syringe. So I'm going to take the plunger all the way down. That's at the second division mark. I'm going to go actually just a little bit more. Then what I want to do is I'm going to want to wipe that tip off to get off any excess that I was just pushing out. I'm going to come over here, and I'm going to inject it through. And so I'm going to push all the way down in until the plunger or till the trigger goes, and then I push the top of the syringe to inject that small little 0.1 microliter. So now we're going to wait for the signal to come out on the computer. It's actually plotting it along the bottom here.
Okay, let's go ahead and take a look at the TLC, thin layer chromatography, part of the experiment. Okay, so for this particular part of the experiment, we're going to be taking a mixture of different analgesics. So our analgesics, remember painkillers, analgesics, fever reducer, are acetaminophen, aspirin, caffeine, and salicylamide. All four of these analgesics are found in over-the-counter medication, typically in various combinations or by themselves. It all depends on the brand that you're buying. But yeah, they're oftentimes found in combinations. And then additionally, we're going to have an unknown. And our unknown is a solution that has 2 or 3 of these unknowns. And we're going to compare results from knowns to unknowns to get their identity. So the way we're going to do this here, and I will show you the actual experiment here in a few minutes. But we're going to take each of the different compounds to make standards. We're going to dissolve them in a little bit of organic solvent. And I think with ethyl acetate, remember right? Yeah, ethyl acetate is the one that we use here. And then we use the capillary tube and spot them on the TLC plate that I showed you guys earlier. We're also going to draw lines, more details later. But we're going to spot all these on here, and then we're going to spot additionally our unknown sample. And then, and as you guys saw in the demo that the stuff climbs to the plate. And then we're looking for the spots. So here I have a schematic on how we're going to do this here. So you're going to draw a spotting line on here with a pencil. And as I showed you guys in the demo, you don't want to use ink because ink will actually move. Pencil does not move with the organic solvents. You are then going to let the solvent run up the plate until it gets roughly towards the top. And then you're going to actually mark how far the solvent went. And then you're going to develop your plate. And then when we develop our plate, we'll see how far up the spots went. And then what we do is we take the distance on how far the spot went divided by the distance on how far the solvent went. And remember that distance is from the spotting line to the spot here, or from the spotting line to the solvent front. Try not to measure from the bottom of the plate. That's technically incorrect. So you want to measure from the spotting line, how far it actually moved on the plate. So there's your equation there. Your RF, ratio to front value, is the distance of the compound divided by the distance of the solvent. And that's all there is to it for TLC analysis. It's quick and crude, but honestly, we typically don't use TLC for this purpose. Typically, in my experience, TLC is used for reaction analysis. And we'll actually see next semester in Chem 242 that you can actually track the formation of a product over time as the spot becomes more pronounced on the TLC plate. But that's a story for another time. Okay, let's go ahead and go to the experiment now and see how this all works. Okay, I think we are now ready to get started. So I'm going to go ahead and start off first by making our analgesic solution that we're going to be analyzing by thin layer chromatography. What I did here ahead of time was I took 4 test tubes and I just put a little bit of each of the different solids in here. I didn't weigh them out or anything. I just took the tip of a spatula was enough. And quite honestly, I think I actually have too much sample for each of these in there, but we'll see how it turns out. So I'm going to go ahead and add about 1 or 2 mils of ethyl acetate. Doesn't need to be exact, just as long as they have some solvent in there. So I'm just going to go ahead and just get a pipette full of ethyl acetate for each one of these. According to this pipette, it should be about, I'm thinking like 4 to 5 mils here, quite a bit, so about half a squirt. Yeah, that looks good. I'm kind of eyeballing it here, guys. Does not need to be exact. And then with a gloved hand, I'm going to go ahead and give it a nice shake after. You could put a stopper on these, but I'm not going to worry. Nothing is dangerous for working with today. These are all over-the-counter analgesics, and ethyl acetate, as you may know, is a significant component of nail polish remover. So nothing too dangerous today. So I'm giving each of these a nice little shake. Once again, I want to be clear on gloved hand for this because it's really easy to get this on your hands here. Some people like to stopper these with their thumb and then shake them really good, but that almost guarantees you get stuff on your hand then. At least when I do it that way, it does. So let's give them a good shake this way. If it's not dissolving really good, you could go ahead and take a spatula and mix up, or you could take another pipette and use the pipette to kind of mix it up. But that's not fully dissolving, but I'm thinking we have enough in solution to get a good analysis by TLC. All right, so that was the caffeine. Here we have the salicylamide. Okay, all the samples are ready to go. I'm going to go ahead and set these aside for now. The solvent should not evaporate too quickly. Okay, for our TLC solvent, we are going to be using, I believe it's 10% acetic acid in ethyl acetate. So to get your 100% acetic acid, we say we use glacial acetic. This is concentrated acetic. It's not actually 100%, but it's concentrated acetic acid. So what I'm going to go ahead and do here is take 20 mils of glacial acetic acid to 180 mils of ethyl acetate, and that should give us our 10%, roughly. I went ahead and pre-measured out the solvents here. So I have 100 mils of our ethyl acetate. So 100, and then I have the 80, measured out 80 as well. So 180 mils of ethyl acetate. Then I'm going to go ahead and add the 20 mils of our glacial acetic acid. That'll give us our 10%. And remember, anytime you're mixing strong acids, you definitely want to take it slow. Don't mix it all at once. Be careful. You definitely should always wear gloves for this. If you're doing this in person, you'll notice a really strong vinegar odor. So this is basically concentrated vinegar that we're working with today. Don't add it all at once. I like to take it slow. Yeah, it's not being overly hot today, so I'm going to go ahead and just add the rest of it in here. If you're mixing acids and it's getting too hot, remember you can always put it on ice to help with that. Typically, if you're making aqueous acid solutions, that's usually more of an issue than when making them with the organics. Okay, that solvent is ready to go. So that's going to be our eluting solvent that we're going to be using for our thin layer chromatography. Need a watch glass. And I like to cover it with a watch glass just to prevent any issues with evaporation. Okay, for the next part here, I'm going to show you guys how to prepare your TLC plates for our samples. So there are a couple crucial details here that might be overlooked that you want to try to avoid. So one of them is when you're writing on the TLC plate, you need to make sure that you use a pencil. Specifically, a old-fashioned, non-mechanical pencil. So two things here. One, we can't use ink, because if you use ink, remember ink is an organic liquid. We have organic solvents. Your ink will actually go in solution. So it turns out that graphite does not dissolve very well in organic solvents. You also don't want to use a mechanical pencil, because these tend to be a lot sharper on the edge, on the point, than your standard ones are. And then if you sharpen this too much, I actually recommend tapping it on the counter a little bit to dull the tip. So you want a dull tip on this, not as too sharp of a tip. So I'm actually going to just tap it a little bit to make sure it's not too sharp. I do want to give you an example of why you don't want to use a mechanical pencil, because I'm just going to draw a line on here, and we'll see what happens. You see that? I scratched the surface there. I'm not sure how well it's showing up on camera, but I actually made some of the silica gel come off of the plate here. So to avoid that, you want to draw softly with a dull tip pencil. Okay. So I'm going to go ahead and draw a line about roughly a centimeter in height from the edge here. So you don't have to be exact here. This doesn't even measure in centimeters. Actually, it's an inch ruler. But I'm just going to eyeball it to be about there. The key is that it's straight across, try not to get it crooked, and then you want to draw a soft, light line on there. Like that. So I barely dragged across it. It's going to be really faint, like so. Okay, and when I label my plate here, I want to label below that line. Sometimes people will put little etch marks where they're going to spot at. I recommend against that because you actually disturb the silica on the plate when you do that. So I'm trying to disturb the silica as least as possible. So I'm going to go ahead and write the first 3 on there. I know the manual shows doing 5 samples on the plate here, but this is honestly too small. I think 3 is ideal for a plate of this size. So I'm going to label it as AC, AS, and CA for this one. So that was AC, AS, and CA. I'm not worried about this part, gouging the silica gel, because I'm actually going to be putting my samples above that point. So I'm still not sure how well that's showing up in camera, but hopefully you can see it. So when I spot them, I'm going to spot them on the line above where I wrote. So go ahead and do that. So here we are going to need a little bit of ethyl acetate. I'm going to put this in here for cleaning in between samples. You don't need very much, just a couple milliliters. That should be plenty. As long as it doesn't evaporate, that should be plenty. And then I recommend that you have a paper towel on standby on the side to help us with the capillary tube. Okay. When working with the capillary tube, make sure you have the correct ones. Being an organic lab, chances are you have 2 different types floating around. You'll have your standard capillary tube and you'll have a melting point capillary tube. Remember, the melting point capillary tubes are closed on one end. We want the regular ones that are open on both ends. In this particular lab, as at least all the CSN labs, we order the smaller capillary tubes, so they're easily distinguishable by size. The small ones are the ones that we want. So the small, teeny ones here. So to sample our plate, I recommend that you practice on a paper towel first. So what you're going to do is touch it into the sample. Some of the liquid will pull up by capillary action, and then you touch it to where you want to spot. So try to get a good view of this. So it doesn't reach quite down enough. What we can do is just angle it a little bit to get it up in there. You just need to touch the liquid, and then you guys can probably see that we have a little bit in the capillary tube now. And I'm going to try to do this so you guys can see it. This might be challenging. Typically you want it flat on the table, but I want you guys to be able to see it. So you just touch it on there. Just barely tap it on there to get a little teeny bit out at a time. You don't want it to spread too far. If your spot becomes too big, then you get pore separations. Okay. That should be enough for that sample. Between samples, you want to rinse this out by touching it into your cleaning solvent and then onto a paper towel and let it fully drain onto the paper towel. So draw up, drain, and you want to drain to a new dry spot each time on the paper towel. And while we're doing this, the spot on here is drying. If you're going to be really particular about this, you could use a different capillary tube for each sample. I'm not going to be that particular today. I'm just aware that some cross-contamination may occur, but the size of the spots will make it really obvious which one was supposed to be for that spot. So just touching it in there. I don't even got you for that one. All right, let's try that again. So this is aspirin. The AS is for aspirin. Okay, I got from that time. Then I'm going to go ahead and do it properly this time. Hope you guys can see an okay view. Let me make sure that we're well within view. Touch. All right. Move that one. We got one more spot for this plate. Okay, the last spot here is for caffeine. Just get a little bit up in there. Just got to touch it onto the liquid and then it sucks up on its own by capillary action. So, just a little bit. Okay, that spot came out kind of big. Hopefully you guys can see that on the camera, but that spot is a little too big. It'll be okay for today's experiment though. It worked just fine regardless. Okay, this needs a few seconds to dry, but while I'm doing that, I can set up my TLC chamber. So in the video here, I'm going to show you guys two different ways to do TLCs in the case that your lab does not have a TLC chamber. So for the first one here, I'm going to use the TLC chamber, and then I'm going to use the makeshift one for the next one. So here's your TLC chamber. It's basically just a glass. It's basically a beach with a watch glass, essentially. When you put your TLC solvent in here, you need to make sure that the height of the solvent is below where that line is going to be at when you put the solvent in there. So you don't want the line to be, the solvent level to be touching that line, because then it's going to mix up all your spots. So to get good chromatographic separation, you need to make sure that your solvent level is below that line. So that's the first thing I check before I run anything, that I have the right solvent level. The lid is necessary for this to keep things from evaporating prematurely. Okay, check if that is high enough. It might be too high. Nope, I think we're at a good height there. So for the next part here, all you do is you just set it in there and then let it run, and then when it runs up the plate, after you pull it out, you need to make sure that you draw a line to where the solvent went up to. Some people will like to pre-mark this and let it run to where the mark's at. I don't recommend that because it's a little bit more restrictive that way. So I'm going to go ahead and set it in here. You could use a pair of forceps, tweezers, but okay. And then you just let that go. They typically take about 10 minutes or so, roughly. So I'm seeing it on the camera very clearly here that solvent is climbing up. If you don't have the lid on there, the solvent will climb up and then evaporate, and it'll continuously do that, and you don't get actual chromatographic separation. So while that's running, I'm going to go ahead and prepare our other plate for our last sample and then our unknown. When handling your TLC plates, make sure that you handle them by their edges. Forgot to mention that earlier. And especially you want to have gloved hands, because if you don't have gloved hands and you're touching the tops on them, the oil from your skin will show up on your TLC. Okay, just like before, I'm going to draw a line across using the correct kind of pencil. That's not the correct pencil, this one is. Oops. That is okay. Okay, this last one's going to be salicylamide, I believe. Oh, SA. And then I'm going to put UN for unknown. right? Always keep an eye on this. This is one of the activity that tests your patience in organic chemistry, because they take a while, but if you just leave it go, if you let it overshoot, you have to redo the whole thing. So it's better just to be patient and hang around while it's running. So now is not the time to take a bathroom break. Okay, that should be enough. Now I'm going to go ahead and get our unknown. I am not sure what is in the unknown, because it is unknown to me as well. I'm assuming it's one of these compounds because it was in the box for this lab. Yeah, is it unknown A? I don't know what it is either, so we're going to find out together. Unknown A. Typically, when I make the unknowns, there are typically 2 of these, and you got to figure out which 2 it is by their RF values. So we'll see. So I'm going to touch it into the liquid here. It's really low level there, but it's okay. Just got to touch the liquid. Yep, I got some. Touch it on the line. Yeah, I think that's good. That's a huge spot there. It's a little too big, I think. Okay. We shouldn't need this anymore. I don't like to throw it away yet, just because I need it again. I got to redo a plate or something. Just got to set it aside. I recommend you never toss anything out until you're done. So you have all your data. All right, we're going to call this one good enough. So the main thing here is that when you pull your sample off, that first thing you do is you mark it up where that solvent line went. If I just let it evaporate on its own, dry up, I won't be able to tell where it went. So looks like we went to up there. So I just did a fine little pencil mark about where it went, and we will develop that here in a few minutes. Okay, so I mentioned earlier when I was doing the last TLC chamber here that I had a more low-tech version way to do this. So I'm going to do the second one the old-fashioned way. We're not going to do the TLC chamber, even though we could, but I want to show you the alternate way. So the alternative method is to use a beaker with a paper towel and a watch glass. So on this part, we have to make sure we have the addition of the paper towel. And the reason why is because of the lip on the beaker here allows solvent vapors to come out, and your solvent will actually evaporate on the TLC plate. So to avoid that, to make sure that you're fully saturated in solvent, you wet a paper towel with your solvent. And I recommend propping that in there about where the opening is at on the beaker. So I have the solvent from earlier. I'm just going to pour some on here to get it wet. And then you don't want to use too much here, because remember we have to worry about our solvent level. So I'm just going to saturate this like so. And then check my height. I think I have enough solvent in there now. This part, you got to be careful here. You don't want the plate touching the paper towel here. So I'm going to use some forceps here, tweezers. Put it in here. Kind of want to just prop it in there so it's not touching the paper towel as best you can. I think I'm epically failing at that right now. Yeah, I think, nope, it's not touching. I'm not sure you can see on the camera, but they're actually not touching. So I'm going to turn it a little bit this way so we can watch it climb, and then don't forget you have to cover it with a watch glass. I don't think any method is better than the other, to be honest. I think the TLC chambers are a little bit easier to use, but I wouldn't say that one is actually better than the other. This is whatever you got access to. All right, we're gonna call this one good enough too. Just like before, make sure that when you take them out that you mark them right away. Do not wait. I've seen so many students do that and they have to do it over because they don't know how far it went. Okay, I'm gonna go ahead and give that a few minutes to dry and then we'll take it over and develop the plates. Okay, so now we're gonna do the part where we develop the plates. As you may see, we can't really see anything on there right now. So the way that we develop the plates here is we use a UV light. It turns out that these particular compounds show up plain as day under the UV light. So we can see there that we have some separations. In order to actually get this data though, you want to go ahead and draw circles around the spots that you see and then bring it back to the bench and measure with a pencil. So I'm just gonna go ahead and draw a little spot in between each of the different spots. I also like to draw a little circle around it too. Just trace them out. And we're gonna measure to the middle of the dots that I'm drawing here. You may notice how big the spots are, and how big the spots are is a function of how much sample you had on there. Okay, so like I said, after this is done, you're drawing them, you go ahead and take them to the bench and measure them with the ruler. Okay, we're now ready to gather our measurements to calculate the RF. Remember, you need the how far the compound went divided by how far the solvent went. So it's ratio front, RF value we're calculating here. So for what I did here was I drew lines across for each one of these where all the spots were. I don't normally do this, but I did it for the sake of the video for you guys can get your measurements. So remember, you want to get the distance from the line I drew to this line for the compound, and then from the line I drew to where the solvent went to. Remember, we don't go by the bottom of the plate, we go by where the line is at, that we drew. Okay, so I'm gonna go ahead and put my ruler on there, and you guys can pause the video and get a measurement. So for the acetaminophen is the first one. So lining it up there. And I'll say about what I think it looks like. Remember, you need to get exact values here. This is looking to me to be about 6.6 centimeter. The next one here, lining up the 0 to this here. This next one here is for aspirin. It appears to me to be about 5.3 or so. I wanted to point out the solvent front line looks to me to be about 6.9. Moving along, we have the last one here. This is for caffeine. I do want to point out that the solvent front is the same for all three samples because they were all on the same plate here. Okay, this looks to me to be about 1.9. It's a little bit over 1.9 for caffeine. So that's the caffeine line there. Okay, same deal for the next two. Remember, the next two are on a different plate, so their solvent front is different. Let's go ahead and get the solvent distance first. And let me grab the salicylamide distance too while we're at it. Okay, there's the one for the solvent front. It looks to me to be pretty much exactly at 6. Let me fix the lighting there a little bit. Yep, hopefully the lighting is showing up okay. Looks to be about 6 here. Sorry, a little bit over. Let me fix that where it's at again. There we go. Yeah, about 6.1. And then the one for salicylamide looks to me to be about little over 4.5. Okay. The unknown sample has 3 spots. Your solvent front is the same. So first spot here appears to be at about 1.3 or so. And then the second spot here looks to be at about 3.2, roughly 3.3. And then the last spot here looks to me to be about 4.4. So at a glance, we can kind of see what our unknowns were. Remember, you need to compare them by actually calculating RFs here. But just kind of getting a glance at them, I'm seeing that the acetaminophen kind of climbed the whole plate. It was right behind the solvent front. We did not see one doing that in this one. So I would say that it looks to me like this first spot is very clearly salicylamide. The second spot here is probably caffeine. I don't know. There also is the possibility that we might have an impurity. So I'm thinking that this one here is an impurity. On the UV plate, it was actually really, really faint. So I'm betting it's probably an impurity. If the RF of that spot does not line up to any of the other ones, it's an impurity. Okay. Before we end it here, I did want to show you there is one alternative way to doing plates here. So let's go ahead and back to the fume hood. Okay, one last thing I want to show you guys about TLC before we move on is sometimes, as you guys might have learned from your freshman chemistry class, that colored compounds are typically caused by d orbitals in inorganic compounds. But it turns out because of organic compounds, we don't really deal with d orbitals all that much, it's just carbon. But you guys will see in Chem 242 next semester that if you have a lot of pi bonds, double bonds in conjugation, that leads to colored organic chemistry. It turns out that in order for a compound to be responsive to UV light, as we just saw, they must contain a chromophore, meaning they typically have a double bond in them. But what do you do if you don't have a double bond? How do we use TLC then? In that case, I'm going to show you guys here that we could have done this instead of the UV light. But you take your plate and you just submerge it into some potassium permanganate. So KMnO4, we just drop it in there and then take it right out and then tap it on here. And we can already see one of the spots developing there. So here we're looking for discoloration. Brown colors are spots here. Yeah, one more popping up over here. They should be in the exact same spots that they were under the UV light. I got too much permanganate on there. Let me get a little bit of it off. We can also see it oxidized in the paper towel there. Yeah, that one there is showing up really nicely. So let me go ahead and do the other one. So once again, you just drop it in there, take it right out, and then touch it onto the paper towel to get the excess off, and then let it dry. For this particular one, just like before, you want to make sure you kind of babysit them a little bit, because if you stain them and walk away, over time this whole thing will become a brownish color, and then you can't see anything. So yeah, I'm only really seeing my pencil marks on there. So this is actually not the best method for these particular compounds. UV is better, but I just want to illustrate this is an alternative if UV is not working for you.